Good morning. Welcome to Chemical World. In last chapters, we discussed about what is matter and what it consists of, and we have understand that matter is made of atoms. And we have also discussed about different states of a substance like solids, liquids and gases. And we understand that how they can be distinguished. And we also learned that how the different mixtures or the solutions can be separated and what are different methods we have. Today we discuss about a chapter called atoms and molecules. Yes, we know that what is meant by atom. We also know that what is meant by molecule. In 19th century, many scientists have curious questions in their mind because they wanted to explore the nature. They wanted to understand how the nature is working. They have got different questions in their mind, like suppose you take an iron rod. It's a very good quality iron rod, and you kept in one place for long time, long days. Then you have seen that the iron rod was rusted because of chemical reactions. Now it become rusted iron rod. Now the question comes in the mind that what happened to weight of the rusted iron rod, whether it increases or decreases comparing to previous iron rod. So weight of rusted iron rod increases or decreases. Another question, suppose you have a charcoal and it has some weight. Now you burn the charcoal. Now what you get? You get ash. Now what happened to weight of the charcoal? After burning, what happened to weight of charcoal? And of course, weight of ash also. And another question. You have wet clothes and you kept in the open area for dry for some time. Then what happened to water inside the clothes? Water in wet clothes after dry, what happened? So these type of questions they got in their mind and they're eating their brain to get to have the answers of those questions. Especially they are very much curious and serious to understand about what happened to the weight of the bodies in the combustion process. Like when you burn the magnesium in the air, what happened to the weight of the magnesium? When you burn the sulfur in the air, what happened to the weight of the sulfur? So in that way, they started thinking, and of course, they have given answers to us. Let me explain you those answers based on a small lab activity. In this lab activity, we're going to test that whether the mass or weight changes before reaction and after reaction cases. Let us see. So lab activity, in this, the lab items required are conical flask, right, test tube, lead nitrate, potassium, iodide, distilled water. Of course, we require a rotating stand also. So, see here, you have taken a conical flask and take a fixed amount of water, say distilled water of 250 ml. So, pour the distilled water of 250 ml in the conical flask. Now add lead nitrate in that water. So now conical flask filled with water, distilled water plus lead nitrate. Lead nitrate a fixed amount, any amount you can take. Any amount means don't take very huge amount, like small amount. Okay, now in this conical flask, take a test tube. It's a test tube. Here also you fill the test tube with 250 ml of water. And mix the water with the potassium iodide, a fixed amount. Now keep the test tube inside the conical flask. So then the conical flask should be very big. Now this inside you have a test tube like this. It's tied to a thread. It is hanging through a thread from outside. So it is inside the conical flask. Right. Now you take the weight of the system, weight of this water lead nitrate solution plus conical flask plus test tube plus the solution of water to 250 ml of water with potassium iodide solution. Take the weight. Let the weight is W1, which is weight of the system before chemical reaction. Yes. Now, second step, what I have to do, you just shake the conical flask so that the test tube will turn clockwise or anti-clockwise, and both the solutions are mixed together. When both the solutions are mixed together, there will be some chemical reaction. Then again take the weight. And the weight is W2, which is weight of the mixture after chemical reaction. So after taking the weights W1 and W2, what you have found? You have discovered that W1 is equals to W2. That is, weight of the system before chemical reaction is equal to weight of the mixture after chemical reaction. Or as in so scientific point of view, if you ask me to say, then I will say that weight of the reactants before chemical reaction is equal to weight of the products after chemical reaction. And this statement actually comes under a law called law of conservation of mass. So law of conservation of mass says that, once again I am telling you, weight of the reactants before chemical reaction is equals to weight of the products after chemical reactions. So here I have used two words, reactant and product. So what is meant by reactant and what is meant by product? Reactant is nothing but these are the substances which are participating in chemical reaction. Product is the output what you got after the chemical reaction. So in this lab activity, the reactants are this conical flask solution, water plus lead nitrate, and this 250 ml of water plus potassium iodide. These are the reactants. When you move the test tube for some time and it is turned clockwise, anti-clockwise, and both the solution is mixed, then the last solution what you got by mixing of these two solutions is the product. So, and you have discovered that these two weights are equal. The activity explaining you that mass remains constant. Conservation is the word we frequently use in sciences, in physics, chemistry and biology. All the scientists were eager to know that which are the physical quantities or which are the quantities which remain constant even though many types of changes are happening in nature. In that course, they have found many physical quantities which remain constant. If in physics, if you see, physics says law of conservation of energy, energy remains constant. Law of conservation of momentum, momentum remains constant. Like that, in chemistry also we have this law called law of conservation of mass. So if you ask me to tell in simple way, I will say that the mass remains constant. Mass remains constant. What will be the chemical reaction? what are the changes have done? But always mass remains constant. It doesn't change. Suppose if you have taken reactants before chemical reaction, 50 grams plus 100 grams of reactants. So total is 150 grams. After reaction also, maybe the product's characteristic will change, but the total mass 50 plus 150, which is equal to 150 grams, remains constant. That is what conservation of mass. So if you ask me to tell me in a statement way, the statement is mass is neither created nor destroyed in a chemical reaction. It means mass you can't create, mass you can't destroy in a chemical reaction. That means mass always remains constant. So what is happening there then in the reactions? Reactions, what happening before chemical reaction, what is the form you have, it is changing after the chemical reaction. For example, you have taken H2, you know that hydrogen plus O2, you know that the oxygen, these are two different types of molecules. Now when you combine them, you will get a different molecule called H2O. Of course, chemical balance I have not taken. But if you see, this hydrogen plus oxygen, these are called reactants before chemical reaction. And this is product after chemical reaction. So how much amount of hydrogen plus oxygen are taking? The total amount of mass is equal to mass of H2O. That is what law of conservation of mass. So if you say that I am getting H2O new mass, you are wrong. And if you say that when I got H2O mass, hydrogen was gone, hydrogen mass was destroyed, oxygen mass is destroyed, you are wrong. Because you can't destroy the mass. You can't create the mass. Only you can change the forms of the mass. So here it is in hydrogen oxygen molecule states. Now it is in H2O state, water state. So in that way, mass is neither created nor destroyed in chemical reaction. So before chemical reaction, total amount of mass what you have the same amount of mass after reaction also. There is another interesting concept relating to law of conservation of mass, and I am so much eager to tell you, according to physics. According to chemistry, it was told that in the reactions, the amount of mass before reaction equal to amount of mass after reaction. It's correct. But it is correct when Einstein's a new concept came to the world, and the concept called mass energy equivalence. Mass energy equivalence tells you that mass and energy are related with each other. Mass is converting into energy, or with the energy you can create the mass. According to point of Einstein, mass energy equivalence, mass can be converted into energy and energy can be converted into mass. It's a new thinking of modern physics. And based on this, he has given very famous law in the world, and you know that, which is E equal to mc square. So here energy is converting into mass, mass can be converted into energy. So what Einstein wanted to tell you that the amount of mass what you have, total amount of mass before chemical reaction, and the total amount of mass what you have after chemical reaction, both are same we discussed. But he's saying that some amount of mass in the product side can be converted into energy. This simple formula, simple conversion made us to create atom bombs, made us to construct nuclear reactors. Take a small example. It's uranium, U-92-235. It is a radioactive element. When it is combined with neutron is generally uranium combining with neutron means you are sending the neutron with a very high speed, and this uranium goes and hit the uranium atom. Then it gives barium plus krypton plus 3 neutrons plus huge amount of energy. Of course, it's not chemically balanced. So here my point of view is that this before reaction, these are the reactants. After reaction, those are the products. And here you are seeing these 3 types of masses plus some energy also. It means plus some mass should be there, but this mass converting the form of energy, that is E equal to mc square, and that energy we call nuclear energy. So this is the basic principle for nuclear fission process. So in that way, in sciences, so many refinery things comes. We can't stick to one point that okay, this law is satisfied means this law is satisfied the whole the year, whole the centuries. But when you do discoveries, when you do rethinking process, in one fine day you will find that maybe this law can be modified to get better results in the world. Next concept, law of constant proportions. Listen carefully. It's a very beautiful law which was proposed by Joseph Proust. He thought that when you take a substance in different resources, then do we have same proportion constituents or not? Like, I'll explain you within a beautiful example. Let us take calcium. No, this is copper carbonate. Let's take in a compound called copper carbonate, which is a mixture of copper, carbon and oxygen. So what he had done, he has taken this sample compound in 2 situations. One is a natural one, natural copper carbonate, and second one is laboratory prepared, artificially he had developed the copper carbonate. Now he wanted to test that whether its constituents like copper, carbon, oxygen, do they have same proportions in natural way and lab prepared way, or do they have different proportions in natural way or laboratory prepared way. He tested, and you know what he got the result? See the board. Weight of natural sample and synthetic sample, means synthetic means laboratory prepared. So if you take the copper, he got 51.35, 51.35, carbon 38.91, oxygen 9.74, 9.74. See the table. Now what do you understand? In natural way, the copper carbonate has these proportions of copper, carbon and oxygen. In synthetic also, they have the same proportions. So that those values surprised him. And he made him to tell to the public that even though the sources are different for a particular compound, the origin is different for a particular compound, and the method of preparation is different for a particular compound, but their constituents proportions are same. For example, if you take water, H2O, which is water, another example I wanted to tell you. So water consists of hydrogen and oxygen, you know. Suppose you have prepared the water in laboratory way, artificially, and you have taken water naturally, and you have found the compositions of hydrogen, oxygen in the water. And what you get? Do you get different composition in natural way and artificial way, or you get the same composition? So this example made you clear that Yes, you get the same compositions of hydrogen, oxygen, either it is obtained in natural way or it is obtained in artificial way. So this is what law of constant proportions. So law of constant proportions says that in a chemical substance, the elements are having fixed proportions or fixed percentages also, you can say, by their weight. So this is the statement. So in a chemical substance, like this is the chemical substance, the elements, means these three elements, having fixed proportions, fixed proportions by their weight. That is what law of constant of proportions. So we have discussed about two laws, law of conservation of mass and law of constant proportions. The question comes in the mind of the scientist that why the laws to be written, why the laws to be expressed in sciences. Yes, laws are very important. Laws tells you that where you have to start, where you have to end, and what are the limitations of a particular phenomena. Because in sciences, you couldn't say that the efficient, the 100% efficient, that this law is right and this law is wrong. Each and every law has limitations and advantages too. So to understand where law of conservation of mass and law of constant proportions are satisfied, this scientist John Dalton proposed 2 points. Number one, for law of conservation of mass, all elements should have extremely small particles called atoms. Yes, already we know this. So to satisfy this law, all elements should have atoms. So it means he is saying that elements consist of atoms, which are the smallest thing existing. Or second, for law of constant proportions, elements consist of atoms should not be dissimilar. See, another interesting thing. We know this statement actually, but when you know something, turning into a statement is what called intelligence. So he's saying that in constant proportions, elements should consist of atoms, like first point. But he told that should not be dissimilar, means all the atoms should be same. All the atoms should have the same mass. Suppose if you take an atom called oxygen, if you take a molecule called oxygen molecule, in the oxygen molecule, how many atoms you are thinking all these atoms should have same mass. In oxygen molecule, you have two atoms, O2 now. The two atoms should have the same mass, like 16 grams, 16 grams. That is what he's saying. So O2 molecule, they have two atoms, O and O, which is OH 16, OH 16. So what is expression that this atom is having mass of 16 grams. This atom is also having the mass of 16 grams. So means atoms should have the same mass and atoms are similar. O2 means I can't say that one atom is oxygen, one atom is hydrogen, then you get O2. You are wrong. When I say O2 molecule, the molecule should consist of similar type of atoms with the same mass. That is the second point explanation. Then he quickly proposed and made a standard to understand about the atoms using a theory called John Dalton's atomic theory. According to this theory, the first point is all the matter, whatever the matter you are seeing in the existing universe is made of atoms. The first point. Second point, atoms neither created nor destroyed in a chemical reaction. You can't create atom. You can't destroy the atom also in a chemical reaction. You know, one interesting thing I will tell you. Today, in the observed universe, we know that the universe is expanding. According to the NASA people and the scientists, what is the observed universe we have? In the observed universe, the number of atoms existing is 10 to the power of 70. It's a very big number. After 170 zeros, still it is increasing. The third point, atoms of same element should have same mass. Obviously, I told you earlier, oxygen molecule consists of two atoms which is having same mass, 16 grams, 16 grams. Now fourth one, in a compound, the elements, okay, in the compound, the atoms of elements should combine in whole number ratio. Whole number ratio. This point is nothing but the point explanation what I have done for law of constant proportions. If you take a water molecule using natural process, using artificial process, what are their constituents like hydrogen, oxygen? What is the proportion they have in artificial? They have the same proportions in natural process also. That is what the fourth point meaning.